Now that we've developed a conditional PMF, P of x given y, and conditional PDF of x given y, you might expect that what's coming next. These are distributions, and these distributions have expected values. So we might be interested in expected value of x given y equals y, or more generally, we might be interested in a function g of xy, which of course is a random variable whose expected value is e of g of x and y, say, given y equals y. So for a function g of xy, we have the conditional expected values. In the discrete case, e of g of x and y, given y equals y. It's the function g of xy averaged over the conditional PMF of x given y. But keep in mind that the conditional PMF of x given y is a function of x for different values of y. So because it's just a function of x, all we're doing is averaging over the possible values of x. In the same way, in the continuous case, we average g of x and y over the conditional PDF of x given y. But this is really, for each y, a function of x. And so this integral is just one-dimensional over all possible values of x. Of course, in both cases, we get a different sum or a different integral depending on the value of y. In case that wasn't clear, let's do a simple example here. So in example 7.15, that was the one where x and y were both discrete from 1 to 4, but the PMF was defined on that lower triangular region. We derived 4 different conditional PMFs. Let's write down one of them right now. If you recall, the conditional PMF of x given y, given that x is 3, was equal to 1/3 for x equals 1, 2, 3, and 0 otherwise. And now, when we find the expected value of y, given x is equal to 3, we simply write this is the sum over all y times the conditional PMF of y given x, of y given 3, and this is just the sum of y equals 1 to 3 of y times 1/3, which is of course 1/3 times 1 plus 2 plus 3, which equals 2. So we see that when y is conditionally a discrete uniform random variable over integers 1, 2, and 3, the expected value is just 2. The point of this simple exercise is just that calculating conditional expected values is exactly the same as just calculating expected values. Once you know the PMF, you just do the usual calculation. The only difference is that this PMF happens to be a conditional PMF. So we just solve for the case when we conditioned x equals 3, and we found the conditional expected value of y, given x is 3, was 2. In fact, there were 3 other PDFs. For instance, when x was 4, y was uniform from 1 to 4. And there we found out that the average, you could do this calculation, is 2.5. The point is that for each x, we had a different conditional PMF for y. And so for each x, we have a different conditional expected value, e of y given x is little x. An important special case to think about these conditional expected values are when x and y are independent. When they're independent, we know that the conditional PMF of x given y doesn't actually depend on y. And thus, we know that it has to be true that when we average x over that conditional PMF of x given y, it also can't depend on y. As a consequence, when x and y are independent, the conditional expected value of x given y is some little y is just d of x. And similarly, when the conditional expected value of y, given x takes on some value, is just d of y. Learning that x takes on a value doesn't change what the expected value of y is. If my words on the last slide weren't clear, we can just simply look at the derivation, and we see that the conditional expected value of x given y takes on the value little y. It's x averaged over this conditional PMF. But this conditional PMF, because of the independence, is equal to the marginal PMF, and this is just d of x. And the same thing goes when the roles of x and y are reversed. And the same thing goes for continuous random variables. In that case, we have that the conditional PDF of x given y is just the marginal PDF of x. So far, expected values and even conditional expected values have been pretty simple. When we first introduced expected values, we just said that the expected value is a property of the probability model. In fact, it's just one number, e of x, that describes the random variable x, or you might say the distribution of the random variable x. However, this is a corner of the book where things get a little bit confusing because when we calculated this expected value, this conditional expected value of x given y is little y, we know that the answer depends on little y. So we can think of this expected value of x given y is little y. We can think of it as some deterministic function g of little y. And in fact, this slide has a little bit of a bug because what we're saying is that this expected value of x given y is little y is a function g of y of the observation y equals little y. And when we say that there's an observation, we're really talking about the sample value, small y, of the random variable y. However, where this gets complicated is in the case where we take the deterministic function, g of little y, and use it and apply it to the random variable y, where we obtain the random variable g of random variable y. This is complicated because g of little y is defined as the expected value of x given random variable y is little y. So when we macro substitute the capital Y over here into the function g of little y in the way that we've done many times before, we obtain the following. We obtain that g of capital Y is the expected value of x, conditional expected value, given y equals y. And this, you should say, well, this doesn't really make any sense. What does it mean to condition on random variable y being random variable y? While this macro substitution doesn't really make any notational sense, what in fact happened here is pretty simple. We started with a deterministic function, g of little y, and we applied it to the random variable y to get a random variable. This is, of course, a random variable. And so we adopted kind of a new notation for this. We call this random variable the expected value of x given random variable y. And the key thing to remember is that indeed this quantity is a random variable. When y is little y, this random variable takes on the value e of x given y is little y. So just to review, this conditional expected value of x given the random variable y is a function of random variable y such that if y takes on the value little y, then this random variable takes on the value of the conditional expected value of x given y is little y. So this definition, if it's confusing, stay tuned, we'll do a simple example. This example corresponded to x and y being uniform on this lower triangular region where x and y are between 0 and 1, but y is always less than or equal to x. And in the previous example, we showed that for each value of y, say this value, then x would be defined as being uniform from y to 1. That is, the 45-degree angle corresponds to the line where y equals x. And so this segment starts at the point y comma y. And we have that x is going to be given a value of y, is x is going to be conditionally uniform from y to 1. So this is one of those moments where perhaps words are simpler and more understandable than math. What we have is that given y is equal to y, x is continuous uniform y comma 1 random variable. And of course, the usual parameters we have for continuous uniform random variables are a and b. And in terms of a and b, we know the expected value. And so we know that the expected value of x, which in this case is expected value of x given y is equal to y. Well, in terms of a and b, that's a plus b over 2. In this case, that's 1 plus y over 2, which is just the midpoint of this range of possible values of x. So once we have this conditional expected value of x given y is little y, the next step is essentially trivial. We just simply take the conditional expected value of x given random variable y, and we substitute random variable y into this expression for little y, and we obtain 1 plus y over 2. At this point, you might be saying, why did we make such a big fuss over this? But in some sense, you're right. If you know the conditional expected value of x given y takes on some value, and it's 1 plus little y over 2, then in fact it's equivalent to say that the expected value of x given random variable y is 1 plus random variable y over 2. More generally, you might say, oh, this lecture has made a big fuss over deriving conditional expected values and conditional distributions, but what's really the point of all this? So in the next part of this lecture, we'll continue and apply these definitions to the bivariate Gaussian probability model, and we'll see it gives us a better understanding of how that model works.